This mini lecture will discuss the fundamental laws that describe the relationships between the properties of gases and introduces a host of equations involving gas pressure, volume, temperature, and the number of moles of a gas. The gas laws described in this mini lecture are often referred to as the fundamental gas laws, as the experiments that led to their discovery occurred fairly early in the field of chemistry, as it was just beginning to take form. In fact, you may recognize some of the faces on this slide from our original history lesson at the beginning of the semester on how our current understanding of atoms came to be. This is because early chemists were fond of doing experiments with gases, mostly because they were relatively easy to measure and observe in the lab. And throughout these observations, several connections were made between the gas pressure, volume, temperature, and number of moles of gases, or really at the time, the amount of gases. Starting with Robert Boyle, dubbed the first chemist, a relationship between the pressure and volume of a specific amount of gas at constant temperature was determined from a simple experiment involving a primitive manometer. On the left, a tube that is closed at one end and open at the other contains a sample of gas within the closed end, which is contained by a column of liquid mercury. As we know from the previous mini lecture, the pressure that the sample of gas exerts on the surface of the mercury leads to the mercury being pushed up the column on the right until the force due to gravity of the column of mercury is balanced by the pressure from the gas. And this pressure can be determined from the difference in height of the mercury column as indicated. Next, more mercury is added to the open end of the tube. This increases the gravitational force of the mercury as there is now more within the column. But since the amount of gas on the left has not changed, then the pressure from the gas is no longer enough to balance the gravitational force of the now larger column of mercury. So the mercury gets pushed higher into the tube on the left side, compressing the gas to a smaller volume. The mercury stops moving when the pressure exerted by the smaller volume of gas matches the gravitational force exerted by the column of mercury, which again can be measured based on the height of the mercury, which you'll notice is now larger than it was before. The table on the right shows the decreasing volume of the sample of gas as the amount of mercury in the column is increased, and it shows the increasing pressure that is measured for the compressed gas as the height increases. The important relationship gained from this is that the volume and pressure of a gas are inversely related to each other. As the pressure of the gas increases, the volume of the gas decreases. Or as the volume of the gas increases, the pressure of the gas decreases. And when these two values are multiplied together, we always get the same value, or written mathematically, pressure times volume equals a constant. This also means that if we change the pressure or volume of a certain amount of gas and keep the temperature constant, then the initial pressure times the initial volume will equal the final pressure times the final volume. And we get this equation that looks very similar to the dilution equation that can be used whenever one of these variables is unknown. Note that for all of the relationships discussed in this mini lecture, it's important to pay attention to which properties are held constant and which are changing. In this case, the temperature and the moles of gas are held constant, which allows us to directly observe the relationship between the other two properties, pressure and volume. Next, Jacques Charles studied the connection between temperature and volume of gases while holding the pressure and the number of moles of gas constant. For example, the red and blue balloons shown here contain the same amount of gas, and the pressure exerted by the gases inside the balloons matches the pressure exerted by the atmosphere on the outside of the balloons. Note that the two balloons are the same size because the amount of gas, the pressure, and the temperature of the balloons are the same initially as we see here. Therefore, they have the same volume because they represent the same conditions. However, when the blue balloon is placed inside the liquid nitrogen dewar, the temperature of the gas inside the blue balloon drops drastically. And when the blue balloon is removed from the liquid nitrogen, it is still very cold. So when we compare the conditions of the two balloons in the picture on the right, they both still have the same amount of gas and the same external atmospheric pressure is being applied. So the pressure on the inside of the balloons must still match that external pressure. But their temperatures are now drastically different, and that has led to the volume being different. Note that the colder blue balloon now has a much smaller volume than the warmer red balloon. The graph on the right plots the relationship between the volume and temperature of the gas, and we see that these two properties are directly proportional to each other. As the temperature increases, so does the volume of the gas, and as the temperature decreases, so does the volume of the gas. This also means that the volume divided by the temperature at constant pressure and a constant number of moles will give a constant value. So for a change in volume or temperature, the initial volume divided by the initial temperature will equal the final volume divided by the final temperature. Note that in all gas law equations, temperature must be given in Kelvin, as that is the SI unit for these mathematical relationships. Next, two different scientists are credited with studying the connection between temperature and pressure when volume and the number of moles of gas are held constant. This experiment is very similar to the last one, but instead of using an elastic balloon that allows for the volume to change and therefore the pressure to remain constant, this experiment uses a rigid container that will maintain a constant volume and attaches a pressure gauge to monitor the changes in pressure. Note that at cooler temperatures, the pressure is low, and as the temperature increases, the pressure does as well. So the same direct correlation exists between pressure and temperature as we just saw between volume and temperature. As temperature increases, so does pressure and vice versa. Therefore, we get a similar equation for the change in pressure or temperature at constant volume and constant moles, where the initial pressure divided by the initial temperature will equal the final pressure divided by the final temperature. And again, the temperature must always be given in Kelvin for this equation to work. The last three fundamental laws that we just saw are sometimes combined into one, referred to as the combined gas law, which is incredibly useful when only the amount of gas is held constant and all three other properties are able to change. Finally, Avogadro studied the connection between volume and the number of moles of a gas when temperature and pressure are held constant. And he noted that the volume of the gas is also directly proportional to the amount of gas. So when the volume or the number of moles of gas changes, the initial volume divided by the initial number of moles will equal the final volume divided by the final number of moles. But what's almost even more important about his studies of this relationship is that it established that the same volume of two different gases at the same temperature and pressure will have the same number of gas molecules, which means that the identity of a gas is not important for all of the relationships we have discussed so far, and therefore different gases will have very similar properties under the same conditions. This will be especially important when studying a mixture of gases, a situation that is common during a chemical reaction involving gases. So, since the connections between gas pressure, volume, temperature, and the number of moles do not depend on the identity of the gas, then this means that 1 mole of any gas at the same temperature and pressure will occupy the same volume. So, a standard set of conditions was established for comparing gases and is referred to as standard temperature and pressure, or STP. When we say a gas is at STP, it means that the temperature is 0 degrees Celsius, or 273 Kelvin, and the pressure is the standard atmospheric pressure of 1 atmosphere. Under these conditions, 1 mole of any gas will occupy a volume of about 22.4 liters. This concludes the second mini lecture for material from Chapter 11. Please note any questions you may have about this material and how it is utilized to solve problems in the suggested end of chapter exercises and the sapling homework for this chapter. Please post any urgent questions on Piazza. I will also take questions on this material during one of our required class meetings, and during that time we will focus more on problem solving for concepts in this chapter.